Good morning, everyone. My name is Howard. I'm a PhD student at a Turbulence Research Lab at University of Toronto. Today, I'm going to talk about some of the different ways in modeling a 3D synthetic jet actuator, also known as SJA, in a Crossflow. So, starting with a bit of background, the underlying physical phenomenon that we're trying to combat is flow separation. So here we have two airfoils. The upper one is a zero angle of attack. The flow is fully attached. We have some very low frequency wig. The sketch below, we have the same airfoil, but at a high angle of attack, AOA. And you can see the flow at the leading edge shortly after as a fully separated, leading to stall airfoil. This has a pretty adverse impact on the performance of the airfoil, since you have a significantly increased drag and reduced lift. There are several ways to combat this. One of the methods is by applying active flow control, and synthetic jet is one of the active flow control device. So the way it functions is pretty similar to a piston, except we don't have any physical mechanical moving parts. The diaphragm is driven by a current instead. And the way it functions is that it alternates between ingestion and expulsion stroke. So during ingestion stroke, it entrains fluid from the external environment into the cavity, and then during expulsion cycle, it shoots a vortex ring out. And the way we apply these synthetic actuators in an airfoil is that we apply an area of them close to the leading edge, usually right before the unactuated separation point. In this case, we're using 3D synthetic jets, 3D circular SJAs. But another method is that you can also apply slot-based SJA or other types of synthetic jet as well. So here we have some smoke visualization that highlights or indicates, showcase the effect of the synthetic jet very well. So on the left with flow control, we can see a basically fully stalled airfoil where have a significant flow recirculation bubble. Applied with adequate SJA controls, the separation is basically suppressed, and then the size of the wig is also a lot smaller. Now, so in an experiment, you just attach the SJAs onto the airfoil, but in numerical, there are different ways of modeling it. So starting with some of the components, we have the cavity of the SJA. The cavity usually houses the diaphragm. The diaphragm can be on the bottom or on the sidewall. And then we have a neck that connects between the cavity and the crossflow region. Finally, the jet slot is what we use to describe the area immediate to the crossflow surface. So there are three primary approaches of modeling SJA. The first is modeling the whole SJA by apply a dynamic mesh. This would numerically model the actual expulsion and ingestion cycle of the diaphragm. This is the physically most accurate way, but it's also the most computationally expensive method. And therefore, another way of reducing the computational cost is by omitting the cavity, where we apply a velocity profile at the bottom of the neck. And in our study, the velocity profile that we applied is known as the Womersley solution. It's a pulsing jet, laminar, pipe flow, analytical solution. This was recently used in a DNS study on investigating SJAs as active turbulators. And finally, the third case is we're also going to apply the Womersley solution onto a jet slot only configuration to see what happens if we omit both the cavity and the neck. So the simulation is run in an open foam. The turbulence model we've used is the LSKE model. This is based on a standard K epsilon model, but then it's applied with damping functions. And we validated both methods, both the dynamic mesh and the Womersley solution approach in quiescent flow with the experiment that we currently the SGS model after in quiescent environment. And then we applied the SJ into Crossflow. The Crossflow is pretty straightforward. It's a duct Crossflow with a velocity inlet, pressure outlet, get a no slip on top and bottom wall. The front and back of the domain is applied a symmetry plane. The free stream velocity is around 7.25 meter per second. Momentum thickness base Reynolds number is at 900. So here we're starting with some instantaneous Q criterion contours, and I've basically put the all three cases next to each other. The bottom one is a whole SGA with dynamic mesh. The middle, the center one is a neck only. Finally, the top one is jet slot only. So overall, all three models actually, or all three methods predicted a tilted vortex ring in the end. However, if we look at between 5 and 10 in a streamwise direction, what we see is that for the neck only and whole SGA method, we have a pair of legs. It's a trolling vortex pair. This actually resembles what we see from a hairpin vortex. The legs where as it convex downstream, it gets stretched. But for the jet slot only case, the leg is actually missing and dissipated a lot quicker. So what we did next, we looked at symmetry plane. So this is a neck only and jet slot only transverse velocity. So alternates between expulsion and ingestion. So red expulsion stroke, blue ingestion. What I want to do is pause here. And so this is, both of them are in phase. And this is ingestion cycle. But then for the jet slot only case, we actually have a reverse flow being shot out, even though the boundary condition being applied explicitly states that it should be removing fluid from the flow domain. And what this has in the impact in a crossflow environment is in a time average context is pretty significant. So if we focus on the blue dot trend, the jet slot only, there's a time average boundary layer profile. It has a significantly greater neo-wall momentum due to the false momentum introduced from the ingestion cycle. Now, the false momentum diffuses or spreads out quite rapidly by 10 diameter downstream of the jet slot. Is giving us a very similar results compared to the other two approaches. I also want to state that in the neck only methods, the results we're getting compared to the whole SGA is near identical. We have a local maximum deviation of maybe 2 to 5%. And however, the computational cost was reduced by 72%, which is very significant since we're no longer applying a dynamic mesh. So at this point, we established that we need to model a part of the neck if we want to obtain good results close to the SGA. And to do that, we've come up with a parameter, which is, we call it the volume ratio, which is defined by the volume you ingested during the ingestion cycle divided by the volume of the neck. So if the volume ratio is less than 1, that means you've modeled more neck than what you're bringing in. If the ratio is greater than 1, that means you're bringing more fluid into the neck than what you're modeling. And then we followed up with a parametric study, and then we ran this in a Crossflow. We had a probe at the jet slot centered. So these are instantaneous velocity, but since it's this URANs, the results are quite periodic anyway. So what I want to point out is the blue trend. That's the shortest neck case with a volume ratio of 8. So we're bringing in 8 times more flow than what we actually modeled within the neck. And we can see that the blue trend has a significantly diverged compared to the results of other greater volume or greater neck height cases. And for 4D and 6D, the results are actually near identical, overlapping. And this is where we can see that for the 4D and 6D cases, both the volume ratio is less than 1. So therefore, we're proposing that in order to have good results and avoid the false momentum, you need a neck volume of less than 1. And to make sure that the dependence is on the neck volume rather than the normalized neck height, we set up 2 more cases in the Crossflow, a narrow case and a wide case. So the narrow is in diameter of the jet slot. So they have the same normalized neck height of 4D, and then we've matched the jet momentum. And how we vary them is that by applying different volume ratio. The narrow case, we apply a volume ratio of 2, whereas the wide, we applied a volume ratio of 0.5. So since we know the problem came from where we applied a boundary condition, and this new narrow and wide case, we're looking at the bottom of the neck, literally the first cell within the computational domain. Now, just to briefly mention again, the narrow case of volume ratio of 2 is where we expect it to fail, whereas the wide of 0.5 is where we expected the boundary condition to be valid. So here we have some phase average streamwise and transverse jet velocity during peak ingestion cycle. The wide case gave us an axisymmetric profile, which is what the Womersley solution prescribes, whereas what the narrow case actually predicted a non-symmetric profile. And if we look at some of the turbulence variables predicted, we have significant TKE and epsilon at the bottom of the neck. Now, the Womersley solution is a laminar analytical solution, so having such high turbulence activity variables at the first cell from the boundary condition, where the boundary condition is applied, indicates the method for the narrow case was not applied correctly, and therefore we concluded that the narrow case had failed. So just to wrap everything up, we propose that a volume ratio of less than 1 needs to be met, which translates to you have to model sufficient neck volume more neck volume compared to what you're bringing in during the ingestion cycle. If you can meet this criteria, then the Womersley solution approach can actually give you very comparable results in a neck-only case compared to the dynamic mesh approach with significantly reduced computational cost. Failing to model sufficient neck volume or omitting the neck entirely rendered your results to be only valid further downstream, and in this case XD of 10. Thank you for listening.